Welcome back. This is the fifth video for Math 9 ASI. My name is Nathanael Holmes. Today we're going to be going over continuity and one-sided limits. So a one-sided limit, we can think of this as just our left-hand limit and our right-hand limit. So when we're looking at our left-hand limit, we're going to denote it like this. And we're only concerned about what's directly to the left of our point C. So looking at our example, we have this function f of x is equal to x squared while x is less than 1, and it's equal to x minus 1 when x is greater than or equal to 1. So say we want to find the limit as x approaches 1 from the left. All we want to do is look at the graph immediately to the left and see what we're approaching, coming up this way, and it looks like we're about to hit y equals 1, so that's our limit. We're equal to 1. And we're not concerned about anything else, anything to the right. That's just, we're going to worry about that with right-hand limits. What you could also do if you're not provided the graph or you don't want to draw it, you can also just think about it in terms of the function. So if we know we're approaching from the left, we know that x is going to be less than 1. So we can actually just plug 1 in here. We're going to get 1 back, and it's going to be the same answer, see? So for right-hand limit, we're only concerned about what's immediately to the right of C. So again, looking at the example, if we're looking at 1, but we're looking at it from the right. So we're coming down this way, and it looks like we're approaching y equals 0. So our limit as x approaches 1 from the right of f of x is equal to 0. Same idea, plugging into the piecewise. If we're to the right, then that means x is greater than or equal to 1. So we plug in 1 here. 1 minus 1 is 0. So it's consistent across. Okay. So we can actually use the left-hand and right-hand limits to find like the actual limits. So if we have that the left-hand limit is equal to the right-hand limit, then we know that the limit exists, and we know that it is equal to L. And on the other hand, if the left-hand limit and the right-hand limit aren't equal, then we know that the limit doesn't exist. So let's look at some examples. Right here, we have g of x is equal to x cubed, but x cannot equal 0. So if you remember from limits, it doesn't matter that we have a hole at 0. Just from the left, it looks like we're approaching 0. And from the right, it looks like we're approaching 0. Both of these limits are the same. So the actual limit is also equal to 0. And looking back at the example from before, since we knew that coming from the left, our limit was 1, and from the right, our limit was 0, those aren't the same, so we know that the limit as x approaches 1 of f of x does not exist. Continuity. So a graph f of x is continuous at point C if the limit as x approaches c of f of x is equal to f of c. So what does that mean? So this is an example of a continuous function. This is just x squared. We know that anywhere on this graph, if we take the limit at any point, we know that it's going to exist, and we know it's going to equal whatever the actual value there is. So a graph f of x is continuous over an interval if every point within the interval is continuous. So you check every single possible point, and if all of those are continuous, then the whole thing's continuous. But we know it's not possible to look at every individual point. So we have some functions that we know that are always going to be continuous. And f of x is continuous everywhere if it's continuous over the interval -infinity to infinity. Say we wanted to check continuity over a closed interval, though. So recall that an open interval we denote as parentheses a comma b. And this is going to include all points between a and b. A is less than x is less than b. But we're not going to actually include a and b in that interval. And the closed interval is denoted a comma b in brackets and includes all points between a is less than or equal to x is less than or equal to b. So you know that the only difference here is that in a closed interval, we're including the endpoints a and b. So if we want to check continuity over a closed interval ab, we can do the following. So we check that f of x is continuous over the open interval a comma b in parentheses. We can do this using left-hand and right-hand limits, compare with the values of f of c. Like I said before, we can't check every single point because there's an infinite amount of points between any interval. But we can look at areas that we think are suspect. Like we know that x squared is going to be continuous in every case, for example. But we would just look for cases maybe in our piecewise or just anywhere we think that there is going to be discontinuity. And then what we want to do is we want to give special attention to the endpoints after we've done that. So at our leftmost endpoint, we know that we can't look at anything to the left of that. That's where we stop. So we take the right-hand limit as we're approaching that. And for our rightmost limit b, we know we can't go any more to the right of that, so we can only check as we're approaching from the left. Okay? Interval of continuity. So the interval of continuity is just describing over what points is a given function f of x continuous. So we can do this in 2 steps. First thing we want to do is find the domain of our function. So what functions can we plug x into it and get a number out? Obviously, a point where our domain wouldn't include a point x is like 0 in the denominator, right? That'd be an example of some discontinuity in our domain. And then after we have what our domain is, we just check if it's continuous over this domain and find maybe certain points that aren't continuous. So let's go ahead and do an example of this right now. So here we have the example from before. So we have f of x is equal to x squared minus 2x plus 1 over x minus 1. So the first thing we want to identify is what is our domain. It looks like we have just about every x point, but we have one thing that x can't be, and that is x cannot equal 1, right? Because if we have 1 on the bottom, we have 1 minus 1, and we're going to end up with 0 in the denominator. So that's one thing. So we can say that our domain is everything between negative infinity and infinity, but x cannot equal to 1. And then we can go ahead and simplify this a bit just to make sure nothing's wrong, or just so that we can have something nicer to look at. If we factor the top, we're going to have x minus 1, x minus 1. That's how we'd factor that. And we have x minus 1 left on the bottom. So one of these is going to cancel out. And then we're just left with f of x equal to x minus 1. But we have to keep in mind our condition, and that's that x cannot be equal to 1. And we have x minus 1 as a simple example, and we know that that's continuous. Normally, it's continuous over every point. So we just need to add in the fact that x cannot be equal to 1. So the way we could write that is open interval from negative infinity to 1. And that's an open interval because we can't include 1. I'm going to union that with another interval from 1 to infinity, open interval. So none of this is closed. They're all going to be open interval. So this is negative infinity to 1, unioned with 1 to infinity. Okay? So please let me know if you have any questions. Come to office hours, leave a comment below. Email me, anything that it's the most convenient to you. I also have a sign-in sheet down below if you guys could take the time to fill that out for me. And yeah, let me know if there's anything I can improve. I want to get better. I want to put out the best videos for you guys. But thank you so much for watching, and I'll see you guys later.